So, wishing a great evening to all of you and a very warm welcome to day 5 of our FTP Modeling and Simulation of Composite Materials, Fabrication, Characterization, and Applications. And we are really pleased to welcome you all back and look forward to an enriching and productive session ahead. And the topic for the first session is Modeling and Simulation of Advanced Machining. And let me introduce the honorable resource person for this session, Dr. Angelos Markopoulos. Sir is a professor at the School of Mechanical Engineering of the National Technical University of Athens and belongs to the Laboratory of Manufacturing Technology. Since 2007, he has worked as a university professor at various institutions in Greece and abroad. And since 2014, he has been a member of the NTUA staff. He is a member of the editorial board of several scientific journals and international conference committees, and is the scientific coordinator of national and European projects. His research covers topics such as precision machining, with a particular focus on high-speed machining, grinding, micro-machining, unconventional machining, and additive manufacturing. And he is an expert in the modeling and simulation of machining processes, including the finite element method and molecular dynamics. In addition, he is the author of more than 200 papers in journals and conferences, as well as books in the above-mentioned field. Finally, he was included in the top 2% of scientists who have the greatest influence in their field of expertise, according to a survey by Elsevier and Stanford. We are really honored to have such a distinguished academician as a resource person. Sir has already joined, and I would like to request, sir, please unmute yourself. And sir, please, we are really good to listen to you. Sir, please.
Thank you very much for the introduction and this warm welcome. I am very happy to be among colleagues from India. I have many friends in India, and I have participated in many PhD committees in India. I always find this PhD very interesting because it is quite a different kind of industry that we are looking at there. Such a powerful industry with that the dynamic always provides new insights, and I'm always happy to have people from India sharing opinions, options, and why not also research. There were several occasions that we have applied for joint research with the Indian colleagues, not successfully so far, but maybe in the near future, because one of my biggest dreams is to one day visit your beautiful country. And of course, I would be very happy if someone from your side could visit also ours. After having said that, I also need to congratulate you for this very interesting event. I have participated, not in all occasions, I have to admit, but a lot of them, and I have seen that there is a very high interest from the audience, which makes the work easier for the people who present. I hope the same will be in my presentation as well. Although I have to admit that my presentation is not so focused on composite materials. It is a rather generic presentation about machining. Of course, machining also has a part in composite materials, and I have included my experience on that in the slides that you will see in the following minutes. But let me say that if you find this work interesting about modeling of advanced manufacturing, I think it is an easy step to make sure that you can apply this to your own research in composite materials. After having said that, and after having listened to you describing my career over the years, I describe myself as a professor of manufacturing processes. And of course, over the years, I have evolved from let's say, traditional machining all the way to additive manufacturing and whatever new advanced non-traditional or non-conventional, as it is usually said, machining is presented in the industry. But interestingly enough, if you look, I am editor in chief and also area editor in two journals, two very well-known journals about modeling and simulation. So probably I should let's say, recompose my title, not as a professor of machining, but rather as a professor of modeling. But nevertheless, I think these are two things that go together, especially in contemporary industry. Uh, 20 years ago, maybe modeling was not so, let's say, embraced by the professionals in the industrial practice, in everyday practice. But nowadays, as we are in a more competing and more, let's say, advanced environment in terms of the productivity and the at the same time high quality that we want to provide, then there is no other way than to look also into research and into modeling and simulation in order to assist ourselves. Having said that, and as an introduction, let me share my uh, slides with you, my presentation. Please confirm that you can see my presentation, that you can hear me clearly.
It is visible, sir.
It is visible. Thank you very much. I also I have some complaints from people from abroad that I speak fast. This is because I am Greek. So if you think that I speak fast, please slow me down. Don't hesitate to do that because I tend, as time progresses, to speak faster. So thank you very much for having me here. Thank you for having an interest in modeling and simulation of advanced machining. As said before, I am a professor of the National Technical University of Athens in Greece, which is the oldest technical university in Greece. You cannot see it here, but there is a date in this spot next to this naked man. This is the date in Greek language, and the date says 1837. If you consider that our state begins in 1821, so it is just after the Greek Revolution that there was a need for such a university to be created. And although we are almost approaching 200 years of life in Greece, we still grow and we still make ourselves, let's say, we have a tendency for extroversy, for turning ourselves to the world rather than stay in Greece. And this is a great opportunity for me in order to participate in these extroversy actions of the university. This is why I have included some slides about the university and the university life, because I would like to share this with you. Please bear with me, it will take like 5 minutes. But some more words about the naked man. This naked man is Prometheus. He is not a god, he's a titan in Greek mythology, almost a god, but something different. And the myth behind Prometheus, which in Greek language means the one who first thinks and then acts. This is what the name means, Prometheus in Greece. You see that he holds a torch. So this Titan, who befriended the gods, because the other Titans were enemies of the ancient gods, he was a friend of theirs because he had not a very clear purpose for that. He wanted to steal the fire from them because only gods knew what fire is. So he took it from them and he gave it for free, actually, to humans, so that humans could survive and humans could thrive. So he actually was not a friend of the gods, but a friend of the humans who played his part as friend of the gods. So this is a symbol for us that an engineer holds some kind of knowledge. This is the torch, and his job is to give this knowledge to everybody, usually not for free, but anyway, uh, everybody deserves this knowledge, and this is why engineers are very important for our world. And having said that, I have to add also that there was a punishment for that because God did not say, he stole the fire. Okay, no big deal. No, it was not like that. So they put him on a mountain, and there was a big bird eating his liver every day. But because he was someone who could not die, his liver would regenerate every day. And this is also the fate of engineers. Every day they have their liver eaten, but still we have to carry on, and still we have to continue giving our knowledge to people. And this is the campus in Athens. The first picture, which is on the top, is the downtown campus. It is rather small. This is why, like maybe 25 years ago, we moved to a more spacious campus near the city center of Athens. It is still within Athens, but not in the city center. And there is much more space for the 9 schools of the National Technical University of Athens to have their laboratories. And they are pretty much because in the National Technical University of Athens, there are 9 schools, as I told you, included. The first ones in 1837 being civil and mechanical engineering, but since then, I will show you in the next slide that there are several others as well. NTUA is a university that follows the continental Europe system for training engineers. This means that we have not adopted what was adopted by many universities in Europe, the 3-year bachelor plus 2 years for master. So here we have a 5-year continuous um, studying in the university in order to become an engineer. There is no option to leave earlier the university with a bachelor. So we go, as we call it, with an integrated master degree at the end of these 5 years. And in order to enter this university, you would need to be Greek and speak Greek language. This is something that we would like to change in the future, because this way we do not have international students. But it is our constitution in our country, and it is very difficult to change it. And this is why we do not rank above number 50 in world university rankings. Nevertheless, even with this deficiency that we do not have any foreign students, we still are very high in the rankings. And I just mentioned QS World Universities rankings, but there are many other rankings at the time, and a lot of them that we are also following very closely. And you will see that our universities at the top places for the world universities, certainly top in Europe, and number 1 also in Greece. I have to also point out here that our diploma stands for 300 credit units, ECTS as we call them in Europe, because it takes into account this integrated master scheme that I talked to you about. Nevertheless, our postgraduate students and our doctoral students can be foreigners. There is no problem with that. So maybe after I have convinced you that it is worth mentioning machining and simulation, and you would like to know more about this, you can check NTUA's web page and see the the postgraduate and the doctoral places that we have there, and maybe you can apply for a place there. And here are the list. I won't go through it. The list of the 9 schools that we have in NTUA. The best one, of course, being mechanical engineering, and manufacturing technology, even the best of them, because I am a professor there, and this is what I usually say as a joke. Research is our main goal. Education is equally important. We have more than 250 European projects, which ranks us 10th in EU organizations, and there are a lot of them. Not 10th in as a country, but as a university. So it is rather important. And of course, we have several distinctions over that, because if the income is of the university is too much from research, you realize that also we have the infrastructure that we would like to have. This is a necessity, let's say, for Greek modern times, because although we are a state university, the support that we get from the state is very low, and so we have to turn and show our expertise to the European Union and get our funding from there. We have staff of 400 professors, more or less, which also means that we have like 15,000 students. We are not a big university in terms of students, because we are only a technical university. But nevertheless, if we look into the technical specialties of other universities in Greece and abroad as well, I would say that we are quite big. And there are a lot of opportunities to visit and do your internship, your postgraduate studies in Greece. And I will not bother you more about this. Let's go and see why machining of advanced manufacturing is important. Actually, why modeling and simulation of machining is important, and how we can take a couple of things together in order to assist ourselves in improving as an engineers. And I will start historically by mentioning that machining is very old. We know we have specimens from ancient Greece, ancient Egypt, India, from China, from all over the world, almost 4,000 years ago. Metallurgy and science that man could manipulate metals in order to produce something. But nevertheless, the systematic study of manufacturing processes, and especially machining, is no more than a century old. A little bit more, let's say. We will start our journey in, let's say, a scientific approach for machining from the beginning of the last century, about the beginning of 900s, the first, let's say, industrial revolution. And probably you have, some of you, if you are into machining, you will recognize the name of Taylor, of Merchant, of people who were the first to establish some laws and give us explanations on how machining was carried out. Nevertheless, in order to model initially analytically, and in the future with numerical methods, the one I'm going to focus right now, and see how this thing has evolved. This procedure did not start before 50 years ago. And this is why, this is the reason actually that we consider that modeling of machining still has, it's not in an infant stage, but still has things to say. Things are still left to be told. It is very closely connected to the materials, to the machines, to actually the computers that we have, so that we can do more sophisticated modeling in the future. And now I am in a very, let's say, pleasant place to say that modern machining and modeling, they go hand in hand in industry, and provide the solutions for the engineers. And why would we like to have machining? So the initial objective was to provide a theory, an explanation, let's say, behind some phenomena that we could see from experimental work, and our brain, which has the ability to see patterns, had realized that there are there. But what is the explanation? What is the real purpose? What is the real reason behind what was happening? So a theory was formed through modeling, tested and validated through everyday practice in life. And one very important thing, using this knowledge to predict the future. Predicting the future is always very useful, believe me. So predicting the future means that we were able to predict cutting performance, optimize cutting performance, use new tools, make industry stronger and better. So as already said, already pointed out, the first models were analytical, equations solved by hand, who could give us, uh, let's say, a semi-empirical solution of what is going on. But soon, when the tools became available, and I am talking about computational tools became available, then some new methods were presented, and one of them, of course, was the finite elements method. So here you can see some of the notable simplified models, starting with Merchant's circle about the forces that are exerted on the tool, which resembles a cone, resembles a wedge tool, actually. Of course, this is a very simple model, but nevertheless, the so-called orthogonal cutting model that is very widely used in machining calculations even today is based on this theory, of course, much more sophisticated. And I have in my mind at least one book, not paper, that speaks against this model and why it is wrong. But nevertheless, because of its simplicity and because of it was the basis for more sophisticated models that came in the future, I think it is important to mention it as it is. Of course, the theory evolved. We have the theory for the shear plane, the shear bands, the shear planes, multiple models that came into existence from gaining more insight from previous models and integrating this knowledge into the future. And you can see also that some of these models are simply qualitative. We do not have any calculations to make there, just a way of thinking on what happens. But this has evolved also much more into taking account more laws of physics and making our models more physical aware. This is a term that is more and more used today because of the artificial intelligence that also has inserted machining and modeling of machining. Because usually artificial intelligence is data driven, it takes data, a black box, and a result. But if we have physical knowledge, then sometimes we have even better results. So in the beginning of the 70s were the first papers that we came into scientific journals about the finite element method and machining. Of course, the finite element method was introduced earlier for other problems of engineering. I'm talking about the specific pair of finite elements and machining. And since then, since the 70s of the last century, there has been an explosion of using this method in producing results. So over the years and with the subsequent increase of computational power, because this plays a very important role, we had several advancements, like for example, the existence of commercial finite element software, or even commercial software that are solely dedicated for machining methods. So you see that there is a growing interest in these methods, And with the tools that we have today, there is an always. I think this is not for me. So, as I said, we have two goals today.
आप जो है
So,
6 महीने बाद से 1 साल बाद से कर लीजिए मैंने कहा आप निकाल दो भी हमारा हाँ क्योंकि हम ऐसे कहेंगे कि आप रिसीव करोगे नहीं 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 बात तो नहीं है अगर मैं इससे ये चीज कह दूंगा तो मुझे 1 साल या 2 साल दिला देगा.
That's not for me. Okay. So finite element models today are for having knowledge on fundamental aspect of material removing mechanism. This means it is a fundamental research, but also, as I told you before, it is always good to predict the future. So we use it for predicting parameters like cutting forces, temperature, stresses. This gives us a very good idea on what actually happens in the material that is deformed and cut at the same time at very high speeds, at high temperatures. And it's not at all easy to see this experimentally. It's very, very difficult to experimentally watch this phenomenon evolve because it is happening very fast, but also hindered under the cutting tool and the chip that is produced. So it would be almost impossible to see how this phenomena evolve if we didn't have these materials. But allow me to say that even for advanced matters that have to deal with how we treat machining, fundamental knowledge is always there, is always important. So I wouldn't say that predicting and optimizing procedure is more important than the fundamental knowledge. So I would give them, let's say, equal value for these two things that we can achieve. Many of you, if you have a background in machining, you already know what orthogonal cutting is. It's a two-dimensional representation of how a wedge is is sliding on a surface and removes material. I say in very quick way. It has, of course, some other aspects as well. This is basic. This is where we started, and this is the first finite element modeling, let's say, procedures that we had to apply in order to see that it works. I'm not going to go into more details in that because it is rather fundamental. If you have any objections, though, I will be happy to answer to any questions. But what I want to point out here is by this modeling, we have realized that in machining there are two deformation zones that need to be taken into account in practice and in modeling as well. So the primary deformation zone is the zone that is ahead of the tool, the cutting tool. This used to be not a zone at the beginning, but a plane, but quickly realized from models and experiments that is not just one plane, it's a whole zone that is deformed in front of the material, in front of the cutting tool. In this area, the material, in this zone, the material undergoes severe change in shape. This means the material tries to resist. We have the so-called hardening of the material because of the strain rates that are applied there. At the same time, the material has elevated temperature because of the high plastic deformation. And there is a secondary deformation zone, which is attached to the chip side of the tool. And because of friction, this area is also of very high temperature. So actually, the problem of modeling cutting is to see what will prevail. Hardening of the material due to strain hardening or softening of the material due to high deformations and high friction between the tool and the chip. And if there are parts of the material that are under the influence of the one, let's say, of the one phenomenon or the other. So this is the initial and most important problem that we have to solve when we model machining. And actually, this is where the problem starts. And I will explain in a few minutes why I'm saying that. So as I said, strain hardening causes material to exert more resistance to being deformed and being cut. Cutting is a deformation in the shear plane, and also the high temperature, because it is of elevated temperature. And it has been shown, and we knew this before modeling, that these two very important parameters also influence many other things in machining parameters, the wear of the tool, the surface characteristics of the part that's being produced. So there is interest in focusing in these two areas. And these two areas are very close to the tip of the cutting tool. So first approach, especially at the times that the computational cost was very important, our computers were not so fast and not so big, we had to concentrate our modeling only where this deformation, severe deformation takes place, and focus on the tip of the tool. And of course, we have to take into account several mechanics about that. I'm not going to go into details. This is out of the question, because I would speak for like 10 hours here if I would do that, and I don't want to bother you so much. But I have here a list of different models that have been introduced about the plane, the shear angle that is present when cutting materials, and which has evolved over the years. And now that we have set the problem, let's see what is the solution. So, finite elements, you would argue. Finite elements would be a solution, because it is a very versatile, very agile method, which is able to solve nonlinear problems. The problem is not purely mechanical, it is thermomechanical. We said there is strain hardening, which is mechanical. There is elevated temperature, which is thermal. And of course, with the change of the parameters of the material, there is a change, also a non-linear change of the properties of the material, because nature is non-linear. So there is non-linearity. And of course, we have to focus, as I said, on the tip of the tool and the formation of the chip. Here, there are two challenges that we have to address, and they are important. When I will talk about this, you will say, okay, this is self-understanding. It is not. Let me give you an example. The first and most basic problem that we have to face when we are modeling machining, actually when we are modeling anything, is to provide accurate data for the model. We have to give input. But this input is, in the machining, most of the times is problematic. And why I'm saying that? You will see in the slides that are coming afterwards that we have to address our material as, let's say, an equation, a constitutive law, as it is called in the language of modeling machining. And this constitutive law will give our software to understand how this material will interact with our tool. The tool is not a big problem, because usually the tool is a rigid body that just flows through the workpiece. So this is not a problem. The problem is with the workpiece. And why it is a problem to give accurate data to this model? Because machining takes place at high temperatures, high speeds, and with severe deformation characteristics. And what we have from our experience what data we have from our experience from the materials is for usually for static tests that we do in our labs, and this is not very accurate. I As I told you in the beginning of my presentation, I am an editor in chief and an area editor for two journals about uh, modeling, and most of the machining papers that I receive and I have to review, they do not take this into account. You need specific data for your model, not any data, because this material is the one that you already have. So provide accurate data, number one. Number two, there is not one finite element method. And what am I talking about? You have to choose between different options in order to find which finite element method is the best one to address the problem that you have, which has to do with the meshing, the time integration, the iteration scheme, if it is implicit or explicit, for example. It has to do with several other problems that you have to somehow solve. It is finite elements, although they have, as I told you, commercial software, and it is rather easy because you see a very good interface, and it's very self-explaining what you have to put there, and press this button and do the calculation. Yes, but our engineering thinking has somehow to give an explanation to the results. And if you have garbage in, then you have garbage out. So you have to be very careful on how you solve your problem, because then you will know that you have the right answer to the solution. So very quickly, finite element for beginners, you take a continuum, you divide it into little pieces. They are the elements. This is a mesh of elements. This procedure is called discretization. The elements speak to each other, connect to each other through nodes. On the nodes, we apply our boundary conditions, the loads, all the parameters that we want to apply to the problem. If it is mechanical, thermal, thermomechanical, whatever, the degrees of freedom are also applied there. The nodes communicate to each other by a way that we say how. And through manipulating one of these elements, one of these tiny elements, then there is, let's say, a wave of changes over the other elements as well. But by doing this for only one very small piece of your geometry is much easier than doing it, and much simpler than doing it for the whole. So what is the drawback is that you have to, at the end of the day, you have to take all the equations from the nodes and solve them at the same time and provide you with a result. Of course, this needs to be done by a computer. And the finite elements have three distinct steps. The first one is the so-called pre-processing, where you give all the data that you want to give for the problem, geometry, the physics that you want to put there, the laws behind it, if it is, as I said, thermal, for example, the boundary conditions and the loads wherever you want them to be. And this will form a matrix equation, then a solution. Usually what commercial software sells is the solution. So it is the solver that they have, let's say, developed over the years, and this solver has some very specific characteristics. And the third step is the post-processing, where you collect all the data. That data can be collected over time or over space, or at the same both at the same time, and then provide different steps, snapshots of what happened during your analysis. The model geometry for machining is usually as simple as orthogonal cutting, but of course today as we have more computational power, as I said, it can 3D models as well can be seen, and I will show you some examples in the slides to come. And you can see that model geometry plays a significant role in machining. We know this from practice, but here is a simple explanation for that. You see that if the tool, for example, is wider, then the primary and secondary deformation zones are also wider. This plays a role on how the material will act and how the chip will be created. And of course, geometry, although some people would say, okay, geometry is given, it's straightforward. Geometry is something that needs to be carefully thought and inserted in the program in order to have the results that you would like. And here are some examples from just growing from orthogonal modeling and giving it a third dimension to oblique cutting, which is a little bit more complicated, or to even more sophisticated 3D problems, where you do not just want your program to give you a result on cutting forces, but also you can see how the product will look like after it has been machined. And of course, the evolution goes with hand in hand with a more rising computational cost, which thank God we can today with our computers that we have in hand, we can accommodate and solve the problems. As you have already figured it out, meshing, applying a mesh on the geometry, is a very important step. And this is why most of the pre-processing tools that we use have an automatic mesher to do this for us. The mesh is not something that can be, let's say, straightforward determined. We cannot say that there are some rules or some specific guidance on how to do it. There are, of course, some hints on what to do. For example, if you see on the picture here on the right, you will see that in the primary and secondary deformation zone, there is a denser mesh than in all the other areas. And why this happens? Because the more fine mesh you have, the more nodes you have, the more equations you have to solve, and this means the more computational cost. But there is a point that you cannot go neither to a minimum nor more than a maximum, because if you go to a minimum, then the mesh won't be able to follow the geometry. If you go to a maximum, then the gain that you will have in accuracy is negligible and it's not worth it, the computational time for that. And this is usually, there is a procedure usually that before going into actual, let's say, evaluation of your model, you do a fine tuning of what the size of your mesh will be, so that you do not overdo it, but at the same time you have the accuracy that is required. This is also very important, and I rarely see this procedure in papers, and I think we should look into it. But nevertheless, what we should point out here is that the size, the number, and the type of the elements, because there are many of them, and I will show you in a few minutes what I'm talking about, these characteristics play also a significant role to the results of our simulation. So where action takes place is in front of the cutting edge of the tool, and in some, let's say, very small amounts of material near the tip of the tool. But this phenomenon is dynamic because the nose, the actual tip of the tool, moves continuously to create the chip. Before that, types of finite elements, just some of them. It's not an exhausting, of course, catalog, and there are peculiarities and I would say innovations in some programs that they have some kind of elements that others don't, and you can integrate their more complicated problems. But you can see that there is a wide range of how nodes communicate with each other. They can be either linear or of higher order, and there can be nodes not only at the edges of the meshes but also in between, so that you get a better interpolation between the edges of the element. And of course, a tool that was used from the beginning in machining was the so-called mesh refinement. So what we do is that we use finer and more elements near the tooltip than on the other volume of or area, depends if it is 2D or 3D, your model of the model that you are working on. Another interesting technique that is used in machining, and I will explain why, is also the so-called adaptive meshing. Adaptive meshing means that you have somehow to make sure that the deformation of your elements is not that big that would make them reverse and give you an erroneous result. But if the elements are very small, and please look in picture number 1, the tip, you can see just a haze of black lines. It's not very clear what it is. So you see these elements are very, very small. So not very big deformations are required in order to make them distort too much. So how can we avoid stopping, killing your simulation because of numerical reasons and not reasons of what actually happens in real life? So there was this technique that was adopted over the years, and it's very common today in many programs, in many software, that after each step is finished in the procedure, a new mesh is applied, which is unique and suitable for the specific time step. And you can see that over the evolution of the phenomenon from 1, 2, 3 to 4, the mesh is finer always in the tip of the tool, and the rest of the geometry is very coarsely meshed, because there is actually no big interest on what happens over there. You would wonder how chip is created. We know how chip is created in real life, but how it's created in finite element method. Usually there is a chip separation criterion that we use, and this depends on the scheme of the finite elements that we would like to use. Is it a geometrical separation criterion, meaning when the tip of the tool is very close to a node, then this node is separated into new nodes, and thus we simulate the creation of the chip? Is it a physical separation criterion? The stress, for example, is there is a threshold. If this threshold is exceeded, then the node again is split it into two different nodes. But there are also methods that the chip is created without a specific separation criterion. It has to do with the topology of the grid. And this was made, actually this third option is, let's say, more realistical, because the other two appear like a zipper opening, and which was not very realistic. But in order to achieve this third method, then we have to apply this continuous remeshing, so that the simulation is as close to reality as possible. And I will elaborate a little bit more in some future slides that you will see. And here are some damage criteria that are applied in the case of there is a need for a damage criterion for the creation of the chip, and the thermomechanical coupling. Actually, thermomechanical coupling is not so easy as it sounds. When I first had my hands on a computer who actually could use a software for finite elements, but this was like 25 years ago. What I was doing in order to have a thermomechanical coupling project was to first run the mechanical problem, then run the thermal problem and integrate them together and see what happens. Today, this is not necessary. There are software that can handle both problems at the same time. And this is rather beneficial in terms of time, but also interaction of different phenomena, because the one has an effect on the other. And what we have to actually do here is provide the right data. As I said, this is the problem number one, meaning the parameters for the machining, the properties for the material, the geometry, a mesh that applies best to the geometry that we have. And if we do all this, then we can do a thermomechanical coupling at the same time. Let me now elaborate a little bit more on what should we prepare, let's say, and have in order to start building a model. What are the information and what is the knowledge that we should have in order to have a very successful model? We will start with material modeling because, as I told you, it's tricky, and also it is fundamental because different materials would require maybe different models, even different scales of machining would require different material modeling. For example, it would be quite different behavior of a material if it was a micro cutting model that we would like to build. And the problem again is that in the primary and secondary strain zones, we have very, as I told you, elevated temperatures and very quickly changing situation on the material deformation. Plastic deformation, not elastic, plastic, so very severe. And the cutting zone is a place resembling hell, let's say, for conditions. And we have, which evolve very fast, and we have to make this real. So material modeling is number one. Over the years, we have a lot of models that have been proposed. Initially, very simplistic ones, then taking into account more and more parameters. Sometimes these parameters need some specific tests in order to assign to them some to assign some properties. And for example, if we want to give material properties, then we would need a split Hopkinson pressure bar impact testing in order to get mechanical properties for the material, which is a very difficult to find installation in laboratories all over the world. This is why results are criticized, and this is the reasons that this happens. So not specialized laboratories, not specialized tests, not a correlation of the right conditions of testing to the identical conditions of machining that we would like to simulate. And over the years, various constitutive models have been proposed Here I mention only a few of them because these are the most used ones. And probably if you have ever come across a modeling of machining, you definitely have come across the so-called Johnson-Cook or JC model, which is the most complete one in terms that it takes into account the deformation characteristics and the temperature characteristics, the strain hardening and the thermal softening that we talked about in previous slides. And you see that if we divide this Johnson-Cook model into the three terms that it consists of, you will see that the tests that we need in order to determine the coefficients for each part are coming from very specific laboratory equipment, and they are not the plain mechanical tests that we do in room temperature with just one uh, testing machine. And here is where I would like to make, let's say, a parenthesis or an upgrade for the presentation about multi-phase materials, because this could also include composite materials that is the main topic of this event that we are now. And it's not only about that, because many materials are multi-phase. For example, ductile iron or some steels which have with distinct bands of carbon or other materials that are inside them. And in order to make this modeling, that means that maybe we have to assign to different parts of the model of the material different constitutive laws or different, at least different properties. And this makes, of course, our job more complicated, but nevertheless more accurate. And this is something that is important. Remember that, for example, machining is always accurate, so you have to have the corresponding accuracy also in models. And here, for example, are some examples that I have gathered from the literature about modeling of composites, where you can see it is either composites with, excuse me, either composites with particles or composites with fibers. It's different kind of modeling and different kind of representation, let's say, in the software that we have to use. And it's one of them. It's kind of a composite material, has the corresponding also geometry, the corresponding meshing and boundary conditions, because you have somehow to give to the software to understand that these different materials, they work with each other. So there is a friction and there is a connection between them. It's not just material that is glued the one next to the other. And this makes, as I said, the analysis much more complicated. So you can see here, for example, a metal matrix material with grains, particle reinforcements, and how it is represented both in terms of geometry and meshing. And here, no, it's the next one, but nevertheless, here is also how the tool deforms the material, creates the chip, and how the chip is different from what we saw in previous slides, because there is a difference on how the chip is evolved. This gives different results also for stresses, for cutting forces, and for the surface characteristics of the material that is left behind. And here a short video. Of course, this is not finite elements. It is something different, which I'm going to talk a little bit about in the coming slides. But I know that there is also a presentation after mine today. And Finally, I have to also add here that if you look into the literature, you will find not only models for orthogonal machining. Orthogonal machining, of course, is the majority as it is in normal machining as well, but you will also find models about drilling of composites, grinding of composites, and all manufacturing processes that exist, and there is an interest in modeling. So now that we have our information on the material and we know how to build this model in terms of geometry and properties for the material, then the next step is to determine a friction model. This also may sound that it is very easy, but it isn't, I assure you. If you look into the literature today, you will see that there is a very simplistic approach on how friction is applied. And there is usually a fine-tuning procedure where you change the coefficient of the friction in order to match your modeling results with the validation data that you have. In my opinion, this is not correct because it is not a general model. You have to adjust it every time to the condition. But the friction is a very, very complicated problem and has to be addressed in a very complicated way. There are, of course, again, some proposals on how friction can be inserted in machining. And let me remind you that I'm talking about the friction between the tool and the chip at the chip edge of the tool, where these two kinds of materials interact together. And usually, what we adopt as an approach here, I hope not the Coulomb anymore, because this is a very simplistic approach, is the approach where in near the tool tip there is a Coulomb coefficient that is almost constant through all the phenomenon that takes place, but there is a slip zone afterwards. We can determine this where this zone starts and stops by several tests, and in this area the coefficient changes dynamically because of the parameters, because of the how the conditions of machining change, and this is usually the most efficient way to address this. If we have these two things, material modeling and friction modeling, then we can add more things if we want, tool wear, for example. This is not straightforward. I mean, the finite elements cannot actually give you the tool wear rate. You have to insert some kind of code there to tell to your software that after this happens, then this tool wear can be visualized, manifested in the procedure. So actually, this is not quite something that can be calculated from the finite elements, but it can be inserted in a certain way, take data from the analysis and provide results. For example, you can see here some results and a diagram of how we can insert this through a subroutine in the program in order to take into account the wear. But wear and surface finishing are not things that can be seen from the finite element models. An important, however, parameter is about cooling. Machining, usually, I would say always in industrial practice, but I have come across some very specific industries that avoid using coolants in order to perform their machining. but nevertheless, there is a very high probability that you will have some kind of cooling in your machining procedure. And this is very, very important because it takes away part of the heat that otherwise would remain in the chip or the tool and would change the situation. Or it has to do with lubrication. So in both cases, it interacts automatically with the first two things that we said, the material modeling and the friction modeling. So usually how do we take this into account? Either we insert thermal boundary conditions in the finite element model, or a more complicated and usually not one software procedure is to use a different kind of modeling, usually the CFD method, in order to simulate how coolant flows around the area of machining and removes heat from from the tool. Give me 1 minute. Thank you. So another important aspect is also the numerical formulation. There are basically two approaches. The Eulerian approach, where the finite element mass is fixed in space, and the Lagrangian approach, where the mass is fixed on the material. And what is the difference, you would argue? How would we know what is most appropriate and what is not? We can explain it in mathematics, but let me give a more, let's say, easy explanation. I'll try to explain it as easy as possible. So in machining, if you use an Eulerian approach, the finite element mass is fixed over a control volume. So you have to pass your geometry through this fixed mass. And this is how you create the chip. This is not so intensive in terms of computational cost, but in order to do that, you would need to know a priori how the geometry will change over time. So you have to have different machining experiments, observe how chip is created, draw this chip into your model, and have your geometry pass through these discrete in time phases of the machining. On the other hand, the Lagrangian approach doesn't need to have a priori knowledge of anything. So the elements are attached to the material. The material interacts with the tool. It is deformed because of this interaction, and the mesh is deformed with the geometry of the material. Here, it seems to be much easier. You require less knowledge, let's say, but again, there is a drawback in this case, that this method fails for severe deformation, as it is the case for machining. So you have to do something there, remeshing, for example. Or you would also need a law, you would also need a modus of creating the chip from step to step. And this is either by giving, as we said before, some criterion in order to do that, or in the arbitrary Lagrangian Eulerian approach called ALE for shorter. This is, let's say, a merging of the two different approaches, where there is one step that is Lagrangian and one step that is Eulerian. And then you change, you skip from one to the other in order to represent the new situation in the next time step, produce the results, and then formulate again in the other method in order to have the result. This approach is more complex in terms of computational cost because you would require more steps to be modeled and also a lot of information to be given. From my experience, the Lagrangian approach is much more common than the others. Nevertheless, there is also the possibility to apply one of these. However, and if you see here some results from the arbitrary Lagrangian Eulerian method, you will see that it produces more smooth results than the other two. Here is also an example of such a simulation. There is also another formulation that can be used, which is called coupled Eulerian Lagrangian. This one is only recently has been appeared and used from the academia in papers, scientific papers about machining. I see it more in deformation, for example, manufacturing processes rather than machining. But nowadays also there are several papers and from distinguished colleagues about this CEL method and in metal cutting. Here we have the benefit of not caring about the large deformations, but again, the problem is the computational cost, because we will have to simulate a much higher volume of material. So let's say that in this case, in this CEL method, each element is like a bottle that contains some liquid. And there are a lot of bottles, the one next to the other, and they communicate to each other. So if you exert a pressure in one bottle, then the contents of it will have to flow to the next one. So this is a rather, again, simplistic way of describing it, but this is how it actually works. So filling the elements that are next to it, to the one that you have some load or boundary condition on it, and this is how you create the mesh for your you create the steps for your simulation. Of course, as I said, because there is a danger of overflow in some elements, because the elements are not distorted, so this is why you don't care about larger formations. So if there is an overflow, so you have to design them bigger, and this means that you would require more capacity for computer power, and sometimes it's not very fine in results as the previous approaches. Nevertheless, it is an interesting approach, and as I told you, I see it more and more in papers nowadays. I will let me not go into much detail about how it is formulated, because it will take some time, and go to the next step, which is about the time integration scheme. So the time integration means that we have either an explicit or an implicit approach. Meaning we either have an accurate result or in a degraded result, or a result that is through iterations. Sometimes the first one is beneficial because it gives us confidence about